Hello everyone and welcome to the Autodesk Robot structural analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. Alright, so in this video we are going to continue talking about the circular staircases, and we are going to basically finalize this project. So I'm expecting it to be a little bit relaxing, not intense as the last video. I think I deserve that because the last video was intense. However, I don't know. I will have the editors he talk to you in the red if it's not the case. So without further ado, let's take a look on our structure. So I'll start with the simplest and go back to the hardest. So first things first, you have of course your dead load and your live loads that were not applied on any of those things. So of course I'm going to remove all my structural systems here and apply the loads, which will, of course, you see it disappeared, but because I have deflection shape, remove the deflection shape and you're back to your normal self. Now, first things first, I haven't had any loads on that thing, so I have to load them. The loads on staircases are consisted of the staircase weight itself, the covering or finishing material, and the live load on the staircase. Now, the live load on the staircase is actually a projected load on the step or the treads, so please notice that, it's very important. And I'm going to use this as projected load for the live load. Now, what is the live load on staircase? It is different than the live load on your story. Allow me to explain. So you see, when you design a structure, you usually select your live load based on code recommendations. For example, the ASCE or ASCE has tables that talk about the live load for different structures. Now, please notice here that on staircases, the live loads, depending on the code you're using, are usually a little bit higher than the live loads on the structural story itself, because the staircases are your evacuation routes, and you need to account for like sudden evacuation events. It depends on the code. For now, I will tell you to research your own code to select the correct live load. I will select me a 5 kilonewton per meter square live load. So I'll go here, say 5 negative. This time it's not global, it's a global projected load because it is perpendicular to the projection of the tread. It's similar to snow, and of course the difference between projected loads and global loads shall be discussed in your engineering studies in the university. Basically, global means on its incline and projected means on the horizontal projection of that thing. Anyway, I'll select those all and well apply me that load. So I'll add that, apply, and now I have them loaded. So we go to our dead loads. I don't know, you have some covering materials. What are those covering materials? Well, you see, and this is important now, this only, the dead load of this, the self weight of this, only covers the thickness of the slab, but there is the tread and riser, and there is also the covering materials on the tread and riser, because maybe you want to cover it with marble or something else. So you should take this into consideration. Also notice that the staircase tread and riser here is already included because there is no riser. The riser itself is a gap. So you need to be careful exactly where to apply. It's not just like we don't apply forces willy-nilly. We actually need to like take a step back and think where I should apply the dead loads as in risers and treads or not. Here it's applicable because the riser and tread was not modeled. Here it's applicable because the riser and tread was not modeled. Here it is not applicable because the riser is a gap and the tread is already the steel plate, similar to here. Of course, you might have covering materials and you might have rails, and I will leave the application of rails for you. Just to show you how it's done, I go to Surface and click on Linear Loads on Edges, and we'll select, for example, let's say that the load of the railing is, I don't know, negative 0.05. I'll add that and apply it here on this edge. Wait, I need to click here. I think I have a bug here. I don't know what exactly is the problem. So let's take on the surface load, select loads on edges, click here and select the edge, only the edge. And now you have an edge load. And this is how you can apply the railing loads if you wish, and you shall. So tell me in the comments if you have the same bug or not, because I'm facing something very annoying here. Anyway, you know exactly how you can put the loads, so I want you to try this at home. All right, so we put our live loads, and we're going to put our dead loads now. So let's think. A small approximation here. So I think the riser, I think, was 18 centimeters, so 0.018. And it's a triangular thing, so this multiplied by the tread, which is I think 0.3 or something, average tread. This is the area multiplied by the step size or length, which is 1.25. Now I'm doing a very huge simplification here because I'm using averages here. This is the volume multiplied by 25 gives you a 1.6 kilonewton per meter. No, this is 1.68 kilonewtons per step divided by 1.25. You get 1.35 as the area load. So I'll apply me a 2 or 2.5. Of course, you are responsible, without restricted load, you're responsible of doing perfect calculations here. For me, I am more like telling you how you should do it and leaving you with the necessary tools that gives you the ability to do the calculations yourself. Of course, you might disagree with me. You want me to do everything, but I want to focus on the more important topics of roboting, modeling, and designing. Of course, please tell me in the comment section if you don't want this, if you want me to really go into step-by-step calculation. I didn't do this. I did this in other structures, for example, towers and silos, because the loads were unorthodox. It was like something new for you. But this is just calculations from any design system you have done before, so I don't think we need to add too much talk to it. Anyway, I didn't apply the covering material here or the steps and treads because it's steel and it already has it included. So, of course, you need to get you an ultimate load. So let's go to load combinations. So how do I do that? I go to loads, load combination, and well, just make me an ultimate load. You don't need to do this actually because the designer will do your ultimate combinations for you, but I'm just doing that for the sake of seeing it. I also want, because I was a little bit wary of the deflections, I want to add me a combination to check the deflections. So load manual combinations, and I will add me a new combination. This is an SLS combination, and I'll add me a 1 dead load and 1 live load onto that. And this is this is where the fun starts, because I want to talk about this, the service limit state, because I have problems with the deflection. You don't believe me? Okay, let's run the analysis and see. All right, so let's take a look on the deflections. So first things first. What is my deflection? If you open the deflection shape, you will get shocked. Wait, what is deflection shape? Yeah, you will get shocked because deflection is 1 meter. Yeah, that happens. So, of course, why is it 1 meter? I will talk about this later, but wait for it. There is more to it, actually. So this doesn't make sense. It needs more improvement here. Let's take a look on the concrete deflection. So I'll go to results and go to maps and ask it to open me the Z map of here. Of course, now the problem is that this affects the scales here. So I have a problem now because you see, because this is so huge, you see very small scales here, but in actuality, it's not small. So I'll open the values now and click on OK or apply, hoping that it fixes something. Yeah, now I see values, which makes a little bit more sense. Now, what are my values? Now, you might have forgotten what your values are. So to show you this, let's open maps first and show you the value. The values are in millimeters, so everything I see here is in millimeters. Now, the reinforced concrete staircase is like well known for its sturdiness and its ability to resist deflection. So you can see the deflections are around 1 millimeter, which is okay-ish, I guess. Of course, what are the things that affect the deflection? The first thing that affects the deflection is, of course, your staircase length. The second thing that affects the deflection is your external diameter. The external diameter of the staircase is what is going to deflect the most. The internal diameter might even deflect upwards, and this is what happened here. This one deflects upwards. As strange as it sounds, it deflects upwards because you have a twisting effect, you have a torsion effect here, which will push this point down and take this point up. It's totally normal and to be expected. This is nothing new and nothing strange. I think the deflections are okay-ish. Of course, you have your own codes like L over 360 or something. Of course, I think L over 360 was for the live load. So check out your codes. Some of them talk about the live load itself. Some of them talk about the dead load itself. Some of them talk about the summation of the deflection. You have to check your codes. Here, just to mention, you have two checks because you have an internal edge and an external edge. and you need to know what the length of those things are. Now, there are equations, because, I mean, remember, the deflection is L over 360 or something, so you need L. Now, this is a cylindrical line, so you can use calculus to find the length if you want, or some equations or something. But if you don't and you want just to be a little bit conservative, then all you have to do is to calculate the perimeter of the circle and ignore that it's actually a cylinder, just or helical thing. So let me calculate that. So I will say 2 multiplied by 3.14 multiplied by r, which is 1.75. It is not a full circle because we modeled 3/4 of a circle to 70 degrees. So this is incorrect. So I have to multiply by 0.75, I guess. So 2 pi r by 0.75. 0.75 gives you the real perimeter. This is L for the external perimeter. The max deflection on the external perimeter is 1.24. 8.24 divided by 360 is the max deflection, which is 22 millimeters. You have 1 millimeter. This is perfectly fine. Also, for the internal one, you have a smaller limit because you have a smaller circle. So now the circle for the internal limit, for the internal circle, is 2 multiplied by pi, 2 multiplied by pi, multiplied by, I think it was half. This is the circle, of course, this is a full circle, but I need 3/4 of it. The answer, 2.3, I think, divided by 360, gives you 0.006, which means 6 millimeters. Now you have here less than a millimeter, so it's okay. But also notice that this is upward deflection, so I don't think that the same deflection limits apply. I'm not really sure. It depends on the structure. So this is the first thing. The second thing here is for the steel staircase. So let's take a look on this mess. So this is bad. Like you have like 6 millimeter and 7, wait, you have 60 millimeter and 70 millimeter and whatnot. This is really bad. But why is that? Well, first of all, my beam is a placeholder and it's a big beam. So I was expecting it to be able to hold itself. But it wasn't. So this came as a surprise for me, to be honest. Like, why? Now, the reason why this is because I think that those plates are really heavy. They are made out of thickness 10 steel. This is odd. Now, I think I have a theory about this because your steps in a steel staircase are not plates, but are like plates with holes, like perforated plates or something. Allow me to explain this. So that's what I'm talking about. Of course, this is spiral.uk, just to show you. Of course, those videos are not supported or sponsored by anyone. You see, when you have cantilever staircases, the idea of having 1.25 meter large steps becomes an impossibility. Also, the steps are made out of wood or some lightweight material because steel itself is heavy. So, like, I wanted to use this with care and use it in smaller spaces and when you have absolutely no other option. So I will leave this for you to think about. For me, I totally disagree and totally do not recommend this. I think I have said the same thing in the first video, but once again, this is yet another reason why not to use it. Of course, you are now waiting for me to say something cool, right? However, I don't want to give up. I want to try something strange and awkward. Of course, this is very dangerous now, and this is an idea that I just got on the fly while I'm talking to you. I want to try suspend this staircase. So I have an idea, and I want you to follow me with this. So might be working, might not. I just want to think outside the box because maybe you would need such a thought later in your life. So I'll cancel everything and delete the mesh. And now I will go here and I'm going to try and make this suspended. So I'll go to nodes or geometry nodes and add me a node in the midpoint. I cannot capture the midpoint, can I? Okay, I think I can. No, this is not capturing midpoint. Okay, never mind. I'll just think outside the box. So let me just create a center. So 1, 2. This is a beam. I will remove it later. I'll go to geometry, nodes. On the center of the beam, I should be able to capture it. I am unable. So that's odd. I'm unable to select it because of a bug, but I don't want to let the bug stop me. So I'll go edit, divide. I divide it into 2 pieces, and now I have forcefully created my point. I'm just a little bit annoyed that it needed me to go through all those extremes to get it. So, well, let's select this, control and select again to remove the selection of that point. So finally, I have my point. Finally. Now let's select the point and let's. Uh, I have to do it manually. Fine. Accept me. I will video edit this. Okay, so with the power of video editing, I was able to divide the edges into halves because I'm preparing it to be suspended. So how do I suspend that? Well, I need to select the nodes. Okay, so I've selected the nodes, and now I'm gonna try to do some magic. So I'll go here to edit, move or copy. I'll move it up 1.5 meters to have a sort of, I don't know, fence or something. So 0, 0, 1.5, I will drag it. If you hit execute, I should get these things. Okay, perfect. So far, so good. So I'll assume this is the ground floor. Also, those look ridiculous. So I'll just quickly give them a circular shape because it doesn't make sense to have it like this. So let's go to sections. I don't know, take a circular shape. I'll do parametric now. 25.4 millimeters diameter and a thickness of 5 millimeters. I'm just assuming something here. Add close, and I'll make all of those become pipes. Those look small. So let's make it 2 inches. Okay, now this looks a little bit more sensible. Now, did we finish? No, I didn't finish because we want now to make it suspended. So how do I suspend that? First of all, here is my pin because this will be fixed to the ground or pinned to the ground. Okay, let's fix it anyway. So let's delete this, select this point and apply, and now it's fixed. And now I'm going to use this and the fact that this is on the story, so this is fixed too. I will use this, in a second, let me just fix this point, to suspend this entire staircase. Now it might not work, but it's worth a try. I don't know if it will work or not. I think it was like 1 meter deflection, so let's take a look if I suspend that. It will not, now spoiler alert, just to not raise your hopes, it will not be that great. Just I'm showing you an idea of what you can do to reduce the deflection. The max deflection is still 1 meter. So, okay, fine. That will not be perfect, but let's take a look what happens if we do this. Now, there is a problem here. I can detect that there is a problem with a node here. So to remedy the problem, let me just check if there are other problems because I added some nodes during the video editing. So I need to check if it's everything right. Yeah, see, there is another problem here. So I can detect 2 problems with my nodes. I have to fix them very quickly. So this and this. So let's remove that. Yes. And let's remove the added node here. This one is the culprit. And I think that one was the culprit too. Yeah, now it's better. Okay, so the final thing we are going to do today is, or hope we can achieve in this modeling thing, is to make a beam and use, which one rectangle? The bigger one. Let's just use this rectangle. Of course, this is only a small little thing I'm doing. So let's suspend it first. I don't like that. I will tell you why when I finish. There's something very dangerous here. I'm doing something really, really dangerous, and I have to explain it to you. Okay, so I think I've done it. Now, if I run the analysis, I think my deflection should be less. I know this looks fantastic, but don't get wrong impressions. This is not good. I will tell you why. So let's run the analysis again, taking a look on the deflection. Now, I'm believing it should be much better. I'm not raising my hopes high, to be honest, but I don't know. Moment of truth, right? Oh, okay, it did get better. Much better than I thought, to be honest. I think that the problem is here. The problem is in this supporting. The supporting is bad. You have very weak supports here. You should support it a little bit in the inside, where you have more things to grab at. So allow me to explain what I mean by things to grab at. Once again, I told you before, I'm totally anti this. I don't like that. But just for the sake of argument, let me support those things now. So in a more stiffer region. So I'm shortening my staircase now. So let's run the analysis just to show you the point. And you can see that those staircases got much better deflection than the others. The reason is because you are grabbing a thicker or stiffer plate instead of the beginning. This is arbitrary, I know. Like cantilever staircases for me are something that I don't use. Of course, the fixations here are somewhat arbitrary. You can make it correctly if you basically make R equals, for example, 0.75, and then fix everything on that path. We have done this before. But for now, I just want to prove a point here, not to model perfectly. So let's take a look. Much better deflection. 70 millimeters, still a lot. but at least the 1000 millimeter deflection are away now. And feel free to tell me what you think in the comment section. Now, there was one dangerous thing I said I need to talk about, which is this. It seems everything is nice and dandy, but there is a big problem here. The big problem you have here is that A, you have moment transfer here. This is under heavy moment. This is under heavy moments. And B, this needs to be larger because it supports the entire weight or half the weight of the staircase. So in reality, I would go here, select a much bigger section for this one, and select me a 10 centimeter with a thickness of 20 millimeters, for example, and add this here, a bigger one, because this is the one that supports the entire load of the staircase. Never forget that. And it's on the buckling, on the moment, it's a mess. Once again, the bug kicks in. I cannot select it, it seems. So I have to do some manual stuff. And now it's there. All right, so this basically ends this cantilever staircase. Once again, I want to emphasize that, hey, I am totally against this. I am not a fan of cantilevered staircases. I'm a fan of spiral staircases, or staircases that look somewhat like this, that have a well-defined supporting structure. But this is something I am against, to be honest. Also notice that my live load on those 4 kilonewtons is somewhat exaggerated because, and it's important to say this, why is it exaggerated for a spiral staircase? Because, first of all, this is not going to be an evacuation staircase. And if it is going to be an evacuation staircase, when we have and this is important now, when we have a staircase in a residential building where you have multiple flats, all of them will escape through that staircase, even if it's a spiral one. But if you have a cantilevered staircase, this is usually between 2 levels in one flat. So the inhabitants of that flat are not going to be of substantial weight. So the deflection here is a little bit over-exaggerated, just to tell you. Anyway, with all the nuances and all the things I've explained, I hope that the picture here is clear for you and that you should avoid cantilevered staircases whenever possible. Okay, so to finalize, of course, we need to talk a little bit about the design. Now, you might be a little bit disappointed here to tell you that for the steel staircase, I will not be discussing the design of it. I will relay you to 2 videos I've explained before. Those will be showing right now on the top right corner. The first video talks about the steel design of elements in a structure because it talks about the beams. And the second video, which will also be showed right now above, talks about the design of plates. And it's a long story where I have this explained von Mises stresses and the failure criteria. So it's quite beneficial to take a look at it. What I will talk about today is also the design of reinforced concrete. Now, I know I've talked about plate design before. You might see this in videos linked above. But this is a little bit different. What do I mean by this? Well, first of all, let me now just do a blind design. So design required reinforcement for slabs and walls. I'll just go blindly do me a design. It's okay. I will take this and basically run the analysis for it. So, all right, so the design is completed, and let's take a look. Let me just first of all zoom this in. You have, of course, the areas in X, Y, positive, negative. Now, negative means bottom or moment negative, and Y also means bottom. Of course, you have positive, which means top, and positive, which means top. Now, how do you design that thing? Like, how do you apply those reinforcements? Because robot is a machine and it's just a software. We are the engineers. We need to read the software and be able to implement it. Now, the problem here is as follows. Look, you have different reinforcements in different regions because the moments change, and you have also torsional and twisting moments. So what you get here, millimeter square per meter, is somewhat needs somewhat your attention, to be honest. So let me explain exactly what I mean by this. What I would do, because it's just a staircase, it's not like a big thing. What I would do is I would select the maximum positive, which is 356, in both directions. This is 330. This is 330, and this is 330. I think this is the minimum. So I would go to 356, which is the maximum, and use this to reinforce my entire staircase. Now notice that YY means remember this was in the first video when I intentionally chose my directions. To remind you, here are my directions. YY means in the length direction of the staircase, and XX means in the lateral direction of the staircase. So XX is the secondary reinforcement, if I want to say it like this, and YY is the main reinforcement of the staircase. You can see it's 356 millimeter square per meter, assuming you're using a phi 12 millimeter cross section. So 0.25 multiplied by pi multiplied by 12 multiplied by 12, almost 130 millimeters square, which means you need 3 phi 12 per meter. This is too low, so let's go to 10. So 0.25 multiplied by 3.14 multiplied by 10, 78. So 356 divided by 78 is around 4.5. So let's 5 bars, which means you're using 1 bar phi 10, 1 bar phi 10 each 20 centimeters. And this is going to be a steel mesh. Now, you will have to use 1 phi 10 each 20 centimeters, and this is going to be a steel mesh. There is no problem with the steel perpendicular to the main direction because just bars. But what about the steel that is curved? Now, here I prepared something for you. Now, this is not really a good workmanship example. You can see all kinds of problems in the formwork. However, I'm still want to show you the steel here. You can see that the steel was done in segments, like it's almost each 20 centimeters. I think it's each 20 centimeters. But you can see the steel was done in segments. You can see the steel is made in pieces. This is something I do not recommend. At least what I want you to tell you is when you have pieces, try to arc the pieces as much as you can. And most importantly, when you have pieces, you will have to make sure that your development length is enough, because otherwise you will have development length failure and the entire staircase comes crashing on our heads. Of course, this is not part of where I work. I just found it on the internet. I thought I wanted to warn about this because I see my eyes see some problems here. Now this is an example of what to do, because the previous one is an example of what not to do. This is a clean example of what to do. You can see that the bars are well bent. Of course, you can see that the reinforcement might be a little bit exaggerated, but that's not a problem. You can still add more reinforcement if you want. And notice that the 1 phi I calculated was on top, so you need to provide the same thing on bottom. So you can see it's like a little steel mesh top bottom that goes through the entire staircase. Please notice you do need top and bottom reinforcement. In some staircases, I see people do just one layer of reinforcement. No, in cylindrical staircases, I am an advocate of having a top and bottom reinforcement because it is under torsion and you need stirrups and a box of steel reinforcement to resist torsion. Please refer to your old education in civil engineering back then. So I am a fan of this. This looks clean, and this is what I would do in real life. So for this, I would use, now I said minimum is 1 phi 10 each 20 centimeters. Personally, if I am the one who is really doing it, I would say 1 phi 12 each 20 centimeters, top and bottom, longitudinal and transverse. So in both directions on both faces. And the lateral direction is something I would stir up, or I would like try to box it together like this, to have one sturdy staircase and reinforced concrete, because it's under torsion, and I'm usually a little bit worried when I see torsion. Anyway, so once again, I'm sorry if this is somehow underwhelming of a video, because it's just a completion of what we've talked before. It's nothing new. So I hope that you enjoyed the video. And of course, if you have enjoyed the video and you think that I deserve a like, share, comments, and subscribe, then please do so, especially subscribing, because subscribing increases the reach of my channel. And don't use cantilever staircases. This is the Civil Engineering Essentials channel, and we will catch you in the next video.